In particular, we're going to introduce functions. And function notation. And as I say, in one sense, this is obviously new. We haven't seen it before in this course. In another sense, this is just familiar material repackaged, because we've spent plenty of time looking at equations, for example, looking at a linear equation, say 2x plus 3. And a function is just, for our purposes, a function is just another way of talking about equations. So a little new notation, a little new terminology, but maybe nothing truly new here. In particular, we're going to think of a function as a rule that takes inputs and assigns them to outputs. And even if this isn't really gonna show up in this class, I suppose I ought to include the condition. It's a rule that takes inputs and assigns them uniquely to outputs. And you can think, going back one frame, you can think that this is basically what we have here. We have a relation between X and Y. And you can think of this as a rule that takes X values and assigns them to Y values. So a statement like when X equals 1, Y equals 5, you could think of as taking 1 and assigning it to 5. You have an X value and a corresponding Y value. And that's precisely what we have now that we're looking at functions. We have a rule, we have inputs, and we have corresponding outputs. All that's really to be done, at least for now, is to get our notation nailed down. Or I suppose we should talk about this word uniquely. All this is saying is that one input cannot have multiple outputs. And this isn't something we have to stress about in this class, because we're going to be studying functions that are given by equations, and the equations are going to guarantee that this condition is satisfied. But what this is saying is, if you think of this as an input 1 being assigned to an output 5, 1 cannot also be assigned to 7. If this input has 5 as an output, it can't then have a second output. So that's all that uniquely is about. And with that, it really is time to try to nail down this notation. So let's look at this via an example. Let's look at the squaring function. So this function is going to take an input and it is going to square that input. And the first thing we need to do is give this function a name. That's a difference between functions and an equation like this. This equation doesn't have a name, but a function has to. And by far the most common name is to call a function f for function. So that f be the name of this squaring function. And you have an input, and our input is going to be a variable. And again, that's just like what we're used to. This equation takes x values and spits out y values. So we have a variable x. Let's call our input x here too. And then we have our output. And our output is the input squared. So if we're calling the input x, the output must be x squared. And now we'll put all that together to get the following notation. We start with the name of the function, f. And then in parentheses, our input variable. And if you're reading this out loud, it's f of x. F of x equals, and on the right side of this equality goes the output. F of x equals x squared. And as I've sort of indicated, this is a very notational thing. From a mathematical point of view, if you look at f of x equals x squared, or y equals x squared, it amounts to the same thing. In fact, we can illustrate that. Let me go to Desmos.com. So if we look at f of x equals x squared, this is what we get in green. If we look at y equals x squared. This is what we get in the purple. And I mean, I don't know. This is perfect. I wish I could. Maybe I can make these lines a little thicker for the back of the room. Yeah. You see, I mean, this purple curve, this green curve, they're exactly the same. Desmos is interpreting f of x equals x squared and y equals x squared as two different ways of saying exactly the same thing. Why would we want two different ways of saying the same thing? Well, this function notation can be useful. It can make it a lot easier to write down otherwise complicated examples. And I'm going to give an illustration of that, just so you won't think that we're wasting your time with this function notation. And we're going to come back to this example. You don't have to copy it down unless you will want to. But the average rate of change formula is something that's easy to write using function notation and awkward to write using y equals notation. So say we have a curve. Let's say this is the graph of f of x. It's also the graph of y equals something. Let's say this is the square root of x plus 1. The average rate of change on an interval is, oof, that is such an ugly square root, but leave it be. The average rate of change on an interval is basically what it says on the tin. It's trying to sort of sum up how quickly this graph is changing. And if you try to write the average rate of change using x's and y's, it's incredibly unwieldy to do. It would be something like y when x is b minus y when x is a divided by b minus a. Writing the exact same thing in function notation, it's f of b minus f of a divided by b minus a. So you see that even though this function notation and this y equals notation might be essentially equivalent, it can make our lives much easier to use function notation. And we will be using function notation for most of the rest of the course. So let's look at another couple of examples to make sure we have this nailed down. Let's say f of x equals x squared plus the square root of x. And we're interested in this function at some value. We're interested in the output when the input is 1 or is 4, let's say. Let's make sure we understand how this works. Whatever we have inside those parentheses is the input. And the input then in this case is x. And you'll notice that the input is also showing up on the right-hand side. So if we're interested in a particular input, say we're interested in an input of 4, well, we want to know what happens when our input is 4. So we write down f of 4. And over here on the right, everywhere that input appears, it gets replaced with the new input. So f of 4 equals 4 squared plus the square root of 4. You see I've replaced both these x's, and this then ends up being 18. Or let's give a story problem. Let's also give an example where we're calling our function something other than f and our input something other than x. We can do all of that at once. Let's look at the drug concentration in a hospital patient T hours after the drug was administered. X is the most common thing to call the input, but T is really common too. In particular, a lot of important functions have time as their input. And it's very common to use T for time in that case. Our output is going to be the drug concentration. And here's a fairly realistic formula. I mean, exactly what this function looks like will depend on the drug, it will depend on the patient. Things like sex, body weight, etc. But a realistic equation might look something like this. C of T, And you'll notice that I've named my concentration function C for concentration. Again, F is kind of the default choice, but it's very common to use other letters when we've got a story problem. Something like C of t equals 0.46 times t divided by 2t squared plus 12.8. Drug concentration formulas often look something like this. We'll talk more about a little more about these later in the course, but since I've got this up here, let's take a look at this on Desmos. And if you are watching a recording of this after the fact, you are not going to see anything at the moment, but I'll share my screen in a bit, assuming that this works. I don't know what that was about, but it's typing, sort of typing now. I don't know if this is gonna work. C P equals 0.46 t. I hope sometimes Desmos is weird when you use variables other than x, but 0.46 t divided by 2t squared plus 12.8. Let me now share this and let me zoom in a little. Or rather, let me adjust the viewing window. That's that x get bigger than that. Let's go there. I think this is a pretty good picture. T has to be positive. We talked about a lot about that. Sometimes a variable is restricted. And this graph makes sense as a drug concentration graph. The drug is administered at that moment. There is no drug in the patient's bloodstream. The drug passes through the body. I'm thanking on the words I'm looking for, but the drug goes through the patient's bloodstream and into the patient. The drug concentration increases, and then the drug concentration eventually starts to decrease. It had better do that, otherwise the drug's just sitting in you for the rest of your life. So this does make sense as a drug concentration graph. Let's ask ourselves a question. And let me, since I've said what the input and output are, let me give myself some room to work on this frame. Let me section off that and ask a question. What will the concentration be after 1 day. And time is being measured in hours here. So I'll write that out as 24 hours. In other words, what is the output when the input is 24? C of 24. And now, I mean, this formula, this expression is maybe a little more complicated looking than this thing here. Thank you for that. But it's handled in the same way. We've got this T as our input, and the T appears over in this equation as well. And if we want the output when the input is 24, we just turn all of these T's into 24. And then we reach for our calculator. Again, any student who's watching this video after the fact is not going to be seeing this. In fact, this is kind of, okay, 0.46 times 24. 0.46 times 24 divided by 2 times 24 squared plus 12.8. Let me briefly just share this for the recording. We press the enter key. Our units here should be percent per liter or something like that. So 0.0095% per liter. And that's because I always like to make students write sentences. Let's not be a hypocrite. Let's express this as a full sentence. And again, I think students struggle with sentences when students do struggle because they won't write down what everything means. So here our input is time measured in hours, and our input is 24. Our output is the drug concentration. And our output we found to be 0.0095. And these sentences, I'm never asking you to conduct deathless prose. I'm basically just asking you to stick these pieces of information together. After 24 hours, the drug concentration is 0.0095% per liter. And that's mostly what I'm going to do, I guess. So here we're given the input and asked for the output. You could at least conceptually go the other way. You could ask, if we know the output, can we find the input? Doing that for a function like this would be pretty complicated. So let's maybe look at something simpler. Let's let the input be the radius of a circle in inches, let's say, and the output will be the area. And as you might or might not remember from school, the function is this. The relationship between area and radius is that the area is pi times the radius squared. And you can ask something like, if a circle has an area of 5 square inches, what is its radius? And I mean, probably half of this problem is just taking that 5 and sticking it into the right place. This 5 is an area, so it's going there. 5 equals pi r squared. And now you can solve this, or maybe you can't. We haven't talked about solving this kind of equation yet, so it would be fine if not, but you could divide both sides of the equation by pi to get 1.592. Equals r squared. And then you can take the square root of that number, and you get about 1.262. But there's no one-size-fits-all way of solving an equation. This we were able to solve with the square root. You could have more complicated equations that would be harder to solve. And that, I think, is what I wanted to show you today. We're actually not through with this section, which is fine. I want to have a kind of quiet day tomorrow. It's right before the test. I don't want to